Good afternoon, everyone. We will wait for 2 more minutes for others to join. If not, we will start the session. Okay, we will start the session. In the meantime, let others join because we will be giving introduction for the first 5 minutes or so. So yeah, we'll start. Now I welcome you all to the problem solving session 3 for the NPTEL course Computational Fluid Dynamics. So the course instructor is Professor Sreenivas Jayanti from the Department of Chemical Engineering, IIT Madras, and myself, Ankara Karthika. I am a research scholar from IIT Hyderabad from the Department of Chemical Engineering. So this is about a problem solving sessions wherein we will have 12 weeks of discussion in which we will be solving problems similar to that week's assignment so that it will be helpful for you guys when you solve the assignment. So now we'll go to the introduction. So this is a 12 weeks course. So the course syllabus is laid out in such a way that you will be having an idea from the basics to somewhat in-depth knowledge on certain concepts as well. So the week one, it was about introduction and calculation of flow in a rectangular duct, and second week it is about calculation of fully developed flow in a triangular duct, and third week it is derivation of equations governing fluid flow, and fourth week it is equations for incompressible flow and boundary conditions, and week 5 it is about basic concepts of CFD, finite difference approximations, and week 6 it is about basic concepts of CFD, consistency, stability and convergence, and week 7 it is about solution of Navier-Stokes for compressible flows, and week 8 solution of Navier-Stokes equations for incompressible flows. Week 9 it is about the solution of linear algebraic equation methods, basic methods, and week 10 it is about solution of linear algebraic equations, advanced methods. And week 11 basics of finite volume method including grid generation, and last it is about turbulent flows and turbulence modeling. So in short, to make you understand what you will be reading throughout the course, in the first 2 weeks I hope you all had a clear understanding of the flow through ducts. The first week it was about rectangular duct, and in the second week it was about a triangular duct. And in this week we will be dealing with derivation of equations governing fluid flow, that is continuity equation and momentum conservation equation, that is mass conservation and momentum conservation equations. So based on these equations only we will be solving the fluid flow in a system by means of CFD approaches. And later on, after you are arrived at the equations, you need to specify the boundary conditions, and later it is about dividing the mesh. So as I mentioned previously also, it is always about dividing the mesh in the like defining the mesh and then later dividing the particular geometry into small meshes. First you define the geometry and divide that into smaller segments called meshes, and in the solution you will be solving equations in all those grids, and later you will post process the solutions. So in all time you cannot get these solutions, like there will be some issues like stability issues, and your solution might not converge. All those things you need to be understanding. So finite difference approximation is a particular division, and later consistency, stability and convergence, it is nothing but wherein you are given the option of choosing the best approach. Like not always you will arrive at the converging solutions, and similarly not always you will be like getting the stable solution. So your mesh and your boundary conditions should be chosen in such a way that your solutions will be correct. So, and week 7 it is about solutions of Navier-Stokes for compressible flows, and later it is about incompressible flows. And this is about solution of Navier-Stokes equations and solution of linear algebraic equations. First one is basic methods, and second one is advanced methods like Gauss-Seidel method, and like so many methods, and Newton-Raphson, like those type of methods you will be seeing. And finally it is about finite volume method and grid generation. Like finite difference approach is what you will be dealing with initially, and later you will be moving on to finite volume approach wherein you generate the grids as well. And lastly it is about turbulent flows and turbulent modeling. So this is a basic layout of the 12 weeks course. So I hope you all had now got to know what it is. And moving on, for the books and references, you have 5 books in total. Five, yeah. The first one is Fezziger and Perick Computational Methods for Fluid Dynamics, and second one is Hirsch Numerical Computation of Internal and External Flows, and third one it is Patankar SV Numerical Heat Transfer and Fluid Flow, and fourth it is Verstig and Malal Sekara and Introduction to Computational Fluid Dynamics, the Finite Volume Method, and last one is Anderson JD Computational Fluid Dynamics Basics with Applications. So I would recommend the last book for beginners. If you are a beginner and want to understand what CFD is about, Anderson JD CFD, the basics with applications, should give you an idea. And for finite volume approach, Verstig and Malal Sekara, an introduction to computational fluid dynamics, finite volume method will be very helpful, and these particular books will also be helpful depending on your interest. So but since I haven't read those books, I can't comment on it. Now moving on to the thing, this week it is week 3. The thing what you will be dealing with and what you are studying is about derivations of equations governing fluid flow. So we need to know what the equations are that is governing the fluid flow. So basically we know that in any system, if the steady state is attained, we can say that there is mass conservation should be satisfied. Like so we have the continuity equations. So the continuity equation for incompressible fluid is given by this. So because density is assumed almost constant, we haven't included it. Only velocity is given, dou u by dou x plus dou v by dou y plus dou w by dou z equal to 0. And coming to momentum equation, in the last class itself we have seen that for momentum equation we have 3 equations: x momentum, y momentum and z momentum. So in the x momentum we have rho into dou u by dou t plus u into dou u by dou x plus v into dou u by dou y plus w into dou u by dou z equal to minus dou p by dou x plus rho g x plus mu into dou square u by dou x square plus dou square u by dou y square plus dou square u by dou z square. Similarly, for the y momentum equation, what we have, what will be varying? Can anyone say? The session will go more interesting if you people are willing to answer. But yeah, in momentum equation we have rho into dou u by dou t plus u into dou u by dou x plus v into dou u by dou y plus w into dou u by dou z equal to minus dou p by dou x plus rho g x plus mu into dou square u by dou x square plus dou square u by dou y square plus dou square u by dou z square. This is x momentum. In the y momentum, we have the velocity component with respect to variation will be v, and therefore the equations become something like this: rho into dou v by dou t plus u into dou v by dou x plus v into dou v by dou y plus w into dou v by dou z equal to minus dou p by dou y plus rho gy plus mu into dou square v by dou x square plus dou square v by dou y square plus dou square v by dou z square. And at last we have z momentum equation, which is nothing but variation of the w velocity component: rho into dou w by dou t plus u into dou w by dou x plus v into dou w by dou y plus w into dou w by dou z equal to minus dou p by dou z plus rho g z plus mu into dou square w by dou x square plus dou square w by dou y square plus dou square w by dou z square. So these are the equations. So these are the three equations, and three momentum conservation equation and one mass conservation or continuity equation for incompressible fluid flow. So just remember these equations. Based on this only we will be solving the problems from this week. So similar to last week, we have few practice problems followed by original problems, that is sample problems for week 4, I mean for week 3. And yeah, I hope it is clear now. So now I guess it is clear. If you have any questions or concerns, please feel free to stop me at any point of time. And yeah, you can ask me questions during the session or even after the session. Both are feasible. Just make sure your doubts are getting cleared, and if you want me to have any feedbacks on these, like, I am happy to take any feedbacks as well if you are if you are willing to give one. So we'll see that at the end as well. So these are the practice problems. First question: choose the correct answers from the options given below. Note that three questions have multiple correct answers each. You need to identify all the correct answers. Marking one wrong choice will not count. Choose the correct answers given from the options given below. Choose the correct answers from the options given below, and you need to identify all the correct answers. Marking even one wrong choice will not count. So there may be multiple correct answers for the each question. So you need to identify those questions first. So the first question is that Newtonian fluid assumption is quite accurate for dash. Newtonian fluid assumption is quite accurate for dash. Option A air, option B water, option C crude oil, option D diesel. I repeat, Newtonian fluid assumption is quite accurate for dash. Option A air, option B water, option C crude oil, option D diesel. So anyone willing to give answer? So the answer is actually there are multiple correct answers for this particular question. So I'll give you that clue. Now you need to identify the answer. So let us just see. I have given a clue, so if you can answer, it will be well and good. Alright, answer I have shown by mistake, I'm sorry. So the answer is actually Newtonian fluid assumption is quite accurate for air, it is true. Second, B water, again it is true. And option C crude oil, which is actually false. And last one, it is diesel. Diesel is also a Newtonian fluid. So why Newtonian fluid? Crude oil is a non-Newtonian fluid because for crude oil, the viscosity changes depending on the applied shear, whereas in Newtonian fluid we cannot see the any viscosity change with respect to the applied shear. So diesel is a Newtonian fluid, whereas crude oil is non-Newtonian fluid. One might think that crude oil, diesel, everything is part from the refinery, so we might think that everything is same and it is not a Newtonian fluid. So chances of crude oil and diesel falling under non-Newtonian fluid in our assumption is high, so we need to be very careful. So first let us see what Newtonian fluid means. Newtonian fluid means that fluid whose viscosity remains constant with respect to the applied shear. If the viscosity changes with respect to the applied shear, the fluid is known as non-Newtonian fluid. So for air, if we see air is the only Newtonian fluid, like in the gaseous form. So air is a Newtonian fluid, and second, water. Water also we know that it is a Newtonian fluid. Its viscosity is constant irrespective of the applied shear. And third one, it is crude oil, and in crude oil it is like has a mixture, so its viscosity changes with respect to the applied shear, so we cannot say it as a Newtonian fluid. So crude oil is a non-Newtonian fluid, and option D, diesel, is also a Newtonian fluid. So in this, Newtonian fluid assumption is quite valid for air, water and diesel. So three things are there: air, water and diesel. Options A, B and D. Option A, air, option B, water and option D, diesel is the right answer. Now we are moving to question 2. In question 2, for a Newtonian fluid, sigma yy is given by dash. Option A, half into mu into dou ui by dou xj plus dou uj by dou xi, and option B, it is half mu into dou u by dou y plus dou v by dou x, and option C, it is mu into dou v by dou y, and option D, none of the above. So if anyone is willing to answer this particular question, you can do so. And the question is very simple one. For a Newtonian fluid, sigma yy is given by dash. Option A, half mu into dou u I by dou xj plus dou u j by dou xi, and half, option B, it is half mu into dou u by dou I plus dou v by dou x plus, and option C, it is dou mu into dou v by dou y. So which is the right answer? So answer is option D, none of the above is the right answer. How? It is because for a Newtonian fluid, sigma yy is given by mu into dou v by dou y into 2 factor will come, or else if it is a pure shear flow, that whole yy component will become 0. So both the options are not given in this particular option. So answer is option D, none of the above is the right answer. Option D, none of the above. And now we are moving on to question 3. In question 3, the advection term in the momentum conservation equation in the x direction for constant property two-dimensional Newtonian fluid can be written as dash. Option A, u into dou u by dou x plus u into dou v by dou y. Option B, u into dou v by dou x plus v into dou u by dou y. Option C, u into dou u by dou x plus v into dou u by dou y. Option D, u into dou u by dou x. So I repeat the question once again. The advection term in the momentum conservation equation in the x direction for constant property two-dimensional Newtonian fluid can be written as dash. So we have seen the momentum conservation equation in the first slide itself, and it is asking for the advection term, and that too for the x direction momentum conservation equation, and in a two-dimensional Newtonian fluid can be written as dash. So answer is option C is the right answer, that is u into dou u by dou x plus v into dou u by dou y. So if we go back, so this is the x direction momentum conservation equation. So actually than this, I can take it and I can put it in the answer. This video is being recorded. I hope you all know that. Question 3. Answer. X direction momentum conservation equation in 2 dimension. So I am not going to write all the equations. I am just going to keep it with one equation only, and this is the 3-dimensional equation. But now I am just removing the third component, that is the z component. So x direction momentum conservation equation in the 2-dimensional would look something like this: rho into dou u by dou t plus u into dou u by dou x plus v into dou u by dou y equal to minus dou p by dou x plus rho g x plus mu into dou square u by dou v square plus dou square u by dou y square. So if we are talking about advective term here, add so this is the advective term. So if we go back and look answer, it is u into dou u by dou x plus v into dou u by dou y. U into dou u by dou x plus v into dou u by dou y. So answer is option C is the right answer. I hope now it is clear. So now going to question 4. The diffusion term in the 2-dimensional y momentum conservation equation is given by dash. Again, the diffusion term in the 2-dimensional y momentum conservation is given by dash. So, option A, mu into dou square v by dou x square plus dou square v by dou y square. Option B, mu into dou square u by dou x square plus dou square u by dou y square. Option C, mu into dou square v by dou x square plus dou square u by dou y square. Option D, mu into dou square v by dou y square. So it is a 2-dimensional equation and we are talking about only the y momentum conservation equation. So on that aspect it is option A. How are we saying it as option A? Because the question is about diffusion term in the 2-dimensional y momentum conservation equation, and it is mu into, here the varying velocity component will be v. So mu into dou square v by dou x square plus dou square v by dou y square is the right answer. Option A is the right answer. I hope it is clear for you guys. So option A is the right answer. Mu into dou square v by dou x square plus dou square v by dou y square. However, I am just giving more full answer. Oh. This is the equation, and therefore y momentum conservation equation in 2-dimension. So this is the equation. So for 2-dimension, we are removing these components. So in this is the advection term. Now for diffusion term, it is like diffusion happening by means of viscous transfer, right? So it is diffusion term is this one, mu into dou square v by dou x square plus dou square v by dou y square. So the diffusion term in the two-dimensional y momentum conservation equation is given by mu into dou square v by dou x square plus dou square v by dou y square. Option A is the right answer. How? Because the whole y momentum conservation equation in two-dimensional looks something like this. Rho into dou v by dou t plus u into dou v by dou x plus v into dou v by dou y equal to minus dp dou p by dou y plus rho gy plus mu into dou square v by dou x square plus dou square v by dou y square. So the diffusion term is this. Because of the viscous stresses, diffusion effects occur. That is momentum diffusion. Momentum transfer due to diffusion. So it is mu into dou square v by dou x square plus dou square v by dou y square. Option A is the right answer. So now these are all the practice problems that we have seen. Now we are going to start with the sample problems. So sample problems are problems that will help you in dealing with the assignments from week 3. So this will help you in submitting the assignments on time. So sample problems is that, and first question is that you find that your company's air-to-air heat exchanger is not performing as well as the one offered by a competitor. Your boss thinks this is because the flow is not distributed well on the cold side and would like you to see if this is the case by doing a CFD simulations. What would your response be? So this is just a generalized question testing your understanding of what CFD is. So option A, you assure your boss that using CFD one can readily verify if the suspicion is justified. Option B, you express your doubt about the accuracy of the CFD simulation given the complexity of geometry, turbulence, etc. Option C, you suggest that an analytical approach is more suitable than CFD. And option D, you would rather do experiments. So I want you all to think and answer because this is the basic thing of why you are doing CFD. So the right answer is you assure your boss that using the CFD one can readily verify if the suspicion is justified. So since I gave the answer, I am going to explain why other options are not right. So the first thing is that it is mentioned that you find your company, we'll read the question once more so that we can be very confident of the answer. So I'll read the question. You find that your company's air-to-air heat exchanger is not performing as well as the one offered by your competitor. So your competitor offered one air-to-air heat exchanger and your product is already in the market. So your product is not performing very well when it is compared with your competitor. So your company might go into loss and therefore you need to find a solution. So your boss is thinking that the flow is not distributed well on the cold side. So heat exchanger, it transfers heat from hot side to cold side. So he is thinking that your flow is not distributed well on the cold side and therefore your boss would like to see if this is the case by doing a CFD simulations, and that your boss is asking you to test that by using a CFD simulations. Then what would your response be to your boss? First, that you assure your boss that using CFD one can readily verify if the suspicion is justified. So there is a suspicion, so it can be verified by using CFD because it is a simple problem wherein you are asked to check the flow distribution in the cold side and check whether it is distributed well, because your company's air to air heat exchanger has just flows and temperature exchange. So you can easily do that by using a CFD simulations, and therefore you are assuring your boss that it can be done and checked if the suspicion is true by using a CFD simulations. That is, you can check if the pipe diameter is proper. All those things, if you check, you can assure your boss that using CFD, one can readily verify if the suspicion is justified. Second one, option A is true. Let us keep it aside. Now we will see why B, C and D are wrong. You express doubt about the accuracy of CFD given the complexity of geometry, turbulence, etc. Geometry will be complex for most of the problems. Turbulence will be there for most of the problems. But because of that, the accuracy of CFD is never compromised. So you can easily say that it is not compromised. So there is no space for you to express your doubt. So option B is false. Option C, you suggest that an analytical approach is more suitable than CFD. Analytical approach is not feasible in this particular condition, because imagine we are solving the system of heat exchanger with cold flow in one side and hot flow in another side, and we are just thinking about the design of the system. So it is not possible to go with the analytical approach. And finally, you would rather do experiments. Again, doing experiments is not feasible. Like, we cannot say whether it is because of that particular reason this particular event is happening, because one thing it is like happening in the large scale, another thing identifying the exact area of issue is difficult. So the answer is option A. You assure your boss that using CFD one can readily verify if the suspicion is justified. So option A is the right answer. Now we will go to question 2. In question 2, it is mentioned that again it is a scenario case study type of question wherein you are asked to find the answer. A client has booked a new catalyst that improves the rate of catalytic chemical reaction and wants you to determine through CFD simulations how much better yield it would give compared to the old catalyst. What would your response be? So what is happening? A client has produced a new catalyst and that improves the rate of chemical reaction and wants you to determine through CFD simulations how much better yield it would give compared to the old catalyst. What would your response be? Option A, you expect CFD to give reasonably correct solution. Option B, you expect CFD would not be of much use because flows with catalytic chemical reaction cannot be handled through CFD. You think CFD could be used but it would not be practical as flow over and through each catalyst particle would need to be simulated. Option D, you expect CFD would be of use in establishing the relative goodness of the new catalyst. So again I give you guys 1 minute time and then we will come back and discuss the answer. So coming back, um, what is asking the question? A client has produced a new catalyst, and that new catalyst is improving the rate of catalytic chemical reactions, and therefore they want us to determine through CFD simulations how much better yield it would give compared to the old catalyst. So we are having a new catalyst in our hands and we want to determine how much better yield it would give compared to the old catalyst. So what would we say? We say that it CFD is better at establishing the or finding the relative goodness of the new catalyst. That is what our opinion will be. Why option A? Given option A that you expect CFD to give you reasonably correct solution. So I mean, here what solution we are talking about is not very explicitly clear. So we can't go with option A. Second option, it is you expect CFD would not be of much use because flows with catalytic reactions cannot be handled through CFD. Again, this is false. We can handle catalytic reactions through CFD. And option C, it is you think CFD would be used but it would not be practical as flow over and through each catalyst particle would need to be simulated. So again, CFD could be used but it would not be practical as the flow over and through each catalyst particle need to be simulated, which is not a case because we generally deal with particulate systems as well, and we, like for example in fluidized bed or in fixed bed, what we determine, we just determine the flow over and through each catalyst particle or the each solid particles we would study there. Similarly here it would be practical to study the catalytic particle flow. So option C is false. Option D, but it is right. We expect CFD would be of use in establishing the relative goodness of the new catalyst. Therefore option D is the right answer. Now, coming to question 3, your friend who is a clinician is working at a large teaching hospital and is thus engaged in research. Wants to collaborate with you in simulating the effect of coronavirus on the lungs and breathlessness that is associated with it. What would your response be? I repeat the question. Your friend who is a clinician is working at a large teaching hospital and is engaged in research activities and wants to collaborate with you in simulating the effect of coronavirus on the lungs and the breathlessness associated with it. What would your response be? So what is asking, a friend of us is engaged in research activities in respect to coronavirus and its breathlessness in the lungs, and they want us to do the safety simulations and find out it. Is it possible is the question, and what would our response be in such situations? So option A, it is let's go ahead with it. It is not too difficult. Option B, it is not that straightforward, but I am sure we can get it right and therefore let us go ahead with it. Option C, it is pretty difficult and it won't be probably useful for this coronavirus, but let us go ahead with it anyway. Option D, count me out. I have better ways of spending my time. So what is your answer and why would that answer be? Is the question. I'll give you guys a minute time and just take that minute to identify the right answer. So actually answer is it is pretty difficult and it won't probably useful for this coronavirus, but let us go ahead with it anyway. So the reason is we'll just go first option by option and rule out options which are not applicable. First one, it is let us go ahead with it. It is not too difficult. This is wrong answer because it is difficult to simulate the effect of coronavirus on the lungs because we need to know the virus progression and immune response and fluid dynamics on the lungs. So, and also we need to know the biological aspects of that virus and how fast it can travel through the cells or lungs or whatever. Therefore, it actually kind of requires the expertise of both the biological side of things and the computational modeling techniques as well. So, it is a complex problem first of all. So let us go ahead with it. It is not too difficult. It is a false statement because it is a complex problem and it requires expertise from both the biological thinking and the computational side. And second one, it is not that straightforward, but I am sure we can get it right, and therefore let us go ahead with it. Second one, it is acknowledging that it is not that straightforward. So that is correct. But in the second sentence, it is mentioned that I am sure we can get it right, and therefore let us go ahead with it. This is kind of false statement. It is not that straightforward, true, but we are not sure we will get it right, and therefore we cannot say that because as I mentioned, virus is a biological thing and we need to know several aspects associated with it before we determine the breathlessness that is associated with it. First is the finding the effect of coronavirus on the lungs. We need to know like the immune effect of the lungs and virus affected regions and virus like multiplication speed and our body response to that, and also fluid dynamics on the lungs we need to know, and there are many other factors involved. So it is not that straightforward, but again we are not sure whether we will get it right, and it is a complex problem so that we cannot say that we will get it right. Third one, it is pretty difficult and it won't probably be useful for this coronavirus, but let us go ahead with it anyways. So as I mentioned, right, it is not easy. It is pretty difficult, but again we cannot say it will be useful for this coronavirus, but why to waste it? We can try. So option C is the right answer. Like it is not straightforward answer, but it is difficult one, but we can say that it might not even be useful, but we can say we can try. So option C is the right answer. Option D, it is count me out. I have better ways of spending my time. So that is not the right way to say things. Like we should try, try, try. Count me out is not the engineering way of saying things when we are in development. It is an interesting problem. You will learn so many things when you do these kind of things, but you might not end up with the required results, but you will end up with so much knowledge. So answer to this is option C is the right answer. It is pretty difficult and it won't probably be useful for this coronavirus, but let us go ahead and do it anyway. Question 4, option C is the right answer. It is pretty difficult and it won't probably be useful for this coronavirus, but let us go ahead with it anyway. Now we are going to question 4. Okay, before going to question 4 is about a case study wherein the associated case is that it is flow through a rectangular or square duct something, and we are just dealing with the questions. We'll see what this particular figure is, and based on this figure only following questions are coming. Figure 1, steady flow through a duct of rectangular cross section with width W, height H and length L. Planes A and D are the inlet and the outlet planes, while planes B and C are at a distance of 0.5 L and 0.9 L respectively. Normal velocity at inlet is uniform, and also L is very much greater than W and L is very much greater than H. So what is given? In this direction it is width, in this direction it is height, and in this direction it is L. Sorry for my line, but in this direction it is L, and till here it is zero point 0.5 times of L, that is exactly at the midpoint, and this is at 0.9 times of L, closer to the outlet. Normal velocity at inlet is uniform and length is very much larger than width and height. So by plane C, flow should be fully developed flow. Right. So this is the question. Now we will go and deal with the, this is the problem statement. Now we will go and deal with the questions. So I hope the statement is clear. Like it is a steady flow through a duct of rectangular cross section with width W in the x direction and height h in the y direction and length in the z direction. And planes A and D are the inlet and outlet planes. And plane B and C are at a distance of 0.5 and zero point 0.9 times L. And normal velocity at inlet is uniform. Okay. Okay, sorry, I didn't check the answers. C and A. Okay, I'll check from now on. Sorry. So the first question from this case is that question 4. A fluid element in figure 1 undergoes which type of strain? Options are like a rotational strain, extensional strain, and shear strain. And option A, it is 1 and 2. Option B, it is 2 and 3. Option C, it is 1, 2 and 3. Sorry, 1 and 3. Option D, it is 1, 2, 3. So the answer to this problem is actually option D, 1, 2 and 3. Like here we can consider it as undergoing all type of strain, rotational, extensional and shear strain. So right answer is option D is the right answer. Option D, that is rotational, extensional and shear strain is the right answer. Now going to question 5. Which of the following statements is true for the fluid in figure 1? So there are few statements. Actually, like can someone is mic is on. Can you just unmute it? Thank you. Okay, and the question 5 is, which of the following statements is true for the fluid in figure 1? So first one, it is viscous stress is proportional to the local deformation rate. Second one, the higher the shear stress, the higher will be the centerline velocity. And third is higher the shear stress, the lower will be the viscosity. So I'll read the question again. Which of the following statements is true for the fluid in figure 1? So the figure 1 is the one in which we saw the flow through the rectangular duct. So the question is about viscous stress is proportional to the local deformation rate. I mean, three statements are given. We need to identify which of them is right. First one, it is viscous stress is proportional to the local deformation rate. And second one, higher the shear stress, the higher will be the centerline viscosity. Third one, it is higher the shear stress, the lower will be the viscosity. So option A, it is 1 only. Option B, it is 1 and 2. Option C, it is 1 and 3. Option D, it is 1, 2 and 3. So which do you think is the right answer? So I repeat the question again. Which of the following statements is true for the fluid in figure 1? Viscous stress is proportional to the local deformation rate. And second one, it is higher the shear stress, higher will be the centerline viscosity. And third one, it is higher the shear stress, lower will be the viscosity. So first option is 1 only. And second one, it is 1 and 2. Third one, it is 1 and 3. And last one, all three statements are right. So if you look at the options, you have 1 is common in all, so 1 is right. And we also know that viscous stress is proportional to the local deformation rate. Stress is proportional to strain. So viscous stress is proportional to the local deformation rate. So out of the second and third options, which one is the, okay, this is 3, not 2, 1, 2 and 3. So out of the second and third, which is the right? The higher the shear stress, the higher will be the centerline velocity. Or third one, higher the shear stress, the lower will be the viscosity, which is right. Can anyone give the answer? Okay, answer is second one is true, third one is false. So 1 and 2 is the right answer. So viscous stress is proportional to local deformation rate. We know that stress is proportional to strain. And second one, it is given that higher the shear stress, higher will be the centerline velocity. So that is also true, like from that only, like when shear stress is high, the centerline viscosity will be high. And third one, it is higher the shear stress, lower will be the viscosity. This is false because higher shear stress, higher will be the viscosity. So it is directly proportional, not inversely proportional. So third statement is false. So 1 and 2 only are right. So from that, option B is the right answer. Option B, 1 and 2 is the right answer. Now going to question 6. In question 6, it is mentioned that with reference to figure 1, if W is equal to 0.004 meter and H is equal to 0.024 meter, length is equal to 1.5 meter, inlet velocity of air given the density is 1.2 kg per meter cube and viscosity is 1.8 into 10 power minus 5 kg per meter second, for an inlet Reynolds number of 1000 would be about dash. So we'll read the question again. With reference to figure 1, if W is equal to 0.04 meter and H is equal to 0.024 meter and L is 1.5 meter. So we have a rectangular duct, and in that duct we are given the 3 dimensions. Like this is the rectangular duct. So H is 0.024, 024, and W is 0.04, and this is point, and the length is 1.5 meter. And what would be the inlet velocity? Inlet velocity of air for an inlet Reynolds number of 1000 would be about dash. So we are given Reynolds number as 1000, and inlet velocity of air is question. And we know the properties of air, that is density is 1.2 kg per meter cube and viscosity is 1.8 into 10 power minus 5 kg per meter second. So first we need to identify what is the inlet velocity of air if its Reynolds number is 1000. So I'll give you a hint here. Reynolds number formula is Re is equal to rho v d by mu. So we know rho, we know, we need to find v and we don't know d, and mu is given and Reynolds number is given. So here if we substitute everything in that equation, we will get the value of inlet velocity of air. Inlet velocity of air for an inlet Reynolds number of 1000 would be about dash. So options given are, we'll see the options first. Option A 0.47 meter per second, option B 0.5 meter per second, option C 0.94 meter per second, option D 2 meter per second. So what are we going to find out? We are going to find the inlet velocity of air whose density and viscosity is given as 1.2 kg per meter cube and 1.8 into 10 power minus 5 kg per meter second, and the Reynolds number is 1000, and we are given the dimensions of the rectangular duct, which is 1.5 meter in length and its height is 0.024 meter and width is 0.04 meter. So now I'll actually solve it in the next slide. In the meantime, you can also solve and put the answer. Oh, sorry. Reynolds number is equal to Reynolds number equal to rho v d by mu. Right, this is the formula for Reynolds number. In this, we know the value of rho is given as 1.2 kg per meter cube is unknown, and D is also not explicitly given, so we'll put question mark for now, and again mu is given as 1.8 into 10 power minus 5 kg per meter second. So first we need to find D. So here it is a rectangular cross-sectional channel, rectangular duct. So D is not explicitly given. So how do we find D? That is diameter of the channel. So for that we are using the hydraulic diameter. So D hydraulic diameter D equal to W into H into h, 2 times of w into h divided by w plus h, and d equal to 2 into 0.024 into 0.04, that is what is given, right? 0.04 into 0.024, sorry, 0.04 into 0.024 divided by 0.04 plus 0.024. So what is the answer that is coming? 2 into 0.04 into 0.024 is 1.2 divided by 0.04 by plus 0.024. It is 0.064 divided by 0.064, 18.75. It is 18.75. Okay. No, something is 0.04, 0.024. 2 into 0.04 into 0.024. Sorry, it is not 1.2, it is 0.00192 divided by 0.064. 0.064. It is 0.03. Sorry for the confusion. So hydraulic diameter, we are finding it as 2 into 0.04 into 0.024 divided by 0.024 plus 0.04. That is nothing but 2 into width of the duct into height of the duct divided by width plus height of the duct. So since it is not a circular duct, circular channel, we cannot use rho v d by mu, that is we cannot use the diameter directly. So we need to find the diameter for the rectangular channel. We are using the hydraulic diameter. For after getting the hydraulic diameter, we can substitute in the Reynolds number. So now coming back to the Reynolds number is equal to 1000 equal to rho is 1.2 into V into D, that thing but 0.03 divided by 1.8 into 10 power minus 5. That is the viscosity. So now we need to have V. So V equal to 1000 into 1.8 into 10 power minus 5 divided by 1.2 into 0.03. So answer is actually 1000 into 10 power minus 1. 1000 into 1.8 into divided by 1.2 divided by 0.03. It is 0.5 meter per second. So when we go back and look at the answer, actually options are option A 0.47 meter per second, option B 0.5 meter per second, option C 0.94 meter per second, option D 2 meter per second. So after calculation we know the value as 0.5 meter per second. So answer is option B is the answer. Option B 0.5 meter per second is the answer. So with reference to figure 1, if W is equal to 0.04 meter and height equal to 0.024 meter, length is 1.5 meter, inlet velocity of air is 1.2, inlet velocity of air is dash. If air density is 1.2 kg per meter cube and its viscosity is 1.8 into 10 power minus 5 kg per meter second, and the Reynolds number is given as 1000. So we know the answer as 0.5 meter per second. So we are just seeing how. So first is that I am just explaining the problem again. So Reynolds number is rho v d by mu. So here rho is nothing but density of fluid and v is velocity of fluid and d is the diameter of the channel and mu is the viscosity of the fluid. So we know a value of density of air as 1.2 kg per meter cube and velocity is unknown and diameter is also unknown because it is a rectangular channel. We know the width and the height of the rectangular channel and also the length of the rectangular channel, but we do not know the diameter of the channel. And mu, that is viscosity, is 1.8 into 10 power minus 5 kg per meter second for air. Like I would suggest you guys to remember the values for viscosity and density of air and water. It will come handy whenever you are solving some problems. So hydraulic diameter D is equal to 2 into W into H divided by W plus H. Since it is not a direct problem, I mean direct pipe channel, circular pipe channel, we are just using the hydraulic diameter. So D equal to 2 into W into H divided by W plus H. So D equal to 2 into W is 0.04, H is 0.024. So 2 into 0.04 into 0.024 divided by 0.04 plus 0.024 equal to 0.0019 divided by 0.064, which is nothing but 0.03 meter. Hydraulic diameter is coming as 0.03 meter. Now in this particular equation we know Reynolds number as 1000, rho is given, v is unknown, d is we found out as 0.03 meter and mu is 1.8 into 10 power minus 5 kg per meter second. So we are substituting everything back. Reynolds number is equal to 1000 equal to 1.2 into v into 0.03 divided by 1.8 into 10 power minus 5 kg per meter second. So we are keeping the unknown in the one side and taking all other terms to the other side. We are getting it as 1000 into 1.8 into 10 power minus 5 divided by 1.2 into 0.03. So answer is 0.5 meter per second. So that is the answer. So I hope it is clear for you now. V equal to 0.5 meter per second is the right answer. Now coming to moving on to the next question, that is question 7. The continuity equation for flow in figure 1 can be written as dash. Option A, dou V by dou Y plus dou W by dou Z equal to 0. Option B, dou V by dou Z plus dou W by dou X equal to 0. Option C, dou U by dou X plus dou V by dou Y plus dou W by dou Z equal to 0. Option D, dou U by dou X plus dou U by dou Y plus dou U by dou Z equal to 0. So it is a simple question. So the continuity equation for the flow in figure 1 can be written as dash. So I hope you can answer this question. If anyone knows, you can put it in there. I'll check the answer now. Like previously I didn't check, but now I'll check. So the question, I repeat, it is the continuity equation for flow in figure 1 can be written as dash. So option A, it is dou V by dou Y plus dou W by dou Z equal to 0. Option B, dou V by dou Z plus dou W by dou X equal to 0. Option C, dou u by dou x plus dou v by dou y plus dou w by dou z equal to 0. Option D, dou u by dou x plus dou u by dou y plus dou u by dou z equal to 0. So if anyone can answer the question, it will be good, because it is a straightforward question and we have also seen the answer multiple times in today's class itself. Okay, answer is actually option C is the right answer. That is dou u by dou x plus dou v by dou y plus dou w by dou z equal to 0. Option C is the right answer, because here it is an generalized continuity equation is what we are using over here. We are not making any changes. So the equation is what we have seen in the first thing itself. Sorry. Dou u by dou x plus dou v by dou y plus dou w by dou z equal to 0. So this equation is what is applicable over there as well. So the right answer is I'll read the case statement again for your clarification. Figure 1, that is this figure, steady flow through a duct of rectangular cross section with width W and height H and length L. So this is X direction, this is Y direction, and this is Z direction. In the Z direction, it is length is L. Now X direction, width is W, and Y direction height is H. And we have 4 planes along the rectangular cross sectional duct. So it is A, B, C and D. So A is the inlet and D is the outlet. B and C are at a distance of 0.5 and 0.9 of the total distance. And normal velocity at the inlet is uniform, and V inlet is given. Normal velocity at inlet is uniform and length is very much greater than width and the height. And one can expect the flow to have become fully developed by plane C. By plane C, flow will be fully developed. So I hope it is clear. Now we'll go to the 7th question. That is what we were seeing. The continuity equation for the flow in figure 1 can be written as dash. Option A, dou v by dou y plus dou w by dou z equal to 0. Option B, dou v by dou z plus dou w by dou x equal to 0. Option C, dou u by dou x plus dou v by dou y plus dou w by dou z equal to 0. Option D, dou u by dou x plus dou u by dou y plus dou u by dou z equal to 0. So here all 3 components come into the picture. Dou u by dou x plus dou v by dou y plus dou w by dou z equal to 0. That is the continuity equation for the flow in figure 1. So answer is option C. Option C is the right answer. Dou u by dou x plus dou v by dou y plus dou w by dou z equal to 0. Now we will go to question 8. In question 8, it is mentioned that the momentum balance equation in the z direction for the flow in figure 1 can be written as dash. The momentum balance equation in the z direction for the flow in figure 1 can be written as dash. Option A, u into dou u by dou x plus v into dou v by dou y plus w into dou u by dou z equal to minus 1 by rho dou p by dou z plus mu by rho dou square u by dou x square plus dou square v by dou y square plus dou square w by dou z square. That is option A. Option B, u into dou u by dou x plus v into dou w by dou y plus w into dou w by dou z equal to minus 1 by rho dou p by dou z plus mu by rho dou square u by dou x square plus dou square v by dou y square plus dou square w by dou z square. Option C, it is u into dou u by dou x plus v into dou w by dou y plus w into dou w by dou z equal to minus 1 by rho dou p by dou z plus mu by rho into dou square w by dou x square plus dou square w by dou y square plus dou square w by dou z square. Option D, none of the above. Actually, there is one small mistake in the equation. I'll just change that and come. So now, can anyone say the answer? Like it is the momentum balance equation in the z direction for the flow in figure 1 can be written as dash. So this is not the reduced equation, I will say that, because if it is a reduced equation, w will be a function of x and y only, like w will not be a function of z. So those terms will vanish. So but in general, the momentum balance equation in the z direction for the flow in figure 1 can be written as dash. So answer is option C, u into dou w by dou x plus v into dou w by dou y plus w into dou w by dou z equal to minus 1 by rho dou p by dou z plus mu by rho dou square w by dou x square plus dou square w by dou y square plus dou square w by dou z square. So this is the general equation. So after which it will be like reduced depending on the conditions. So the momentum balance equation in the z direction for the flow in figure 1 can be written as in option C. That is u into dou w by dou x plus v into dou w by dou y plus w into dou w by dou z equal to minus 1 by rho dou p by dou z plus mu by rho dou square w by dou x square plus dou square w by dou y square plus dou square w by dou z square. So this is question 8. Now we will go to question 9. So in question 9, what we have is that for fully developed flow, for a fully developed flow, the steady state momentum balance equation reduces to dash. For a fully developed flow, the steady state momentum balance equation reduces to dash. Option A, dou square w by dou x square plus dou square w by dou y square equal to constant. Option B, dou square w by dou y square plus dou square w by dou y square equal to 0. Option C, dou square w by dou z square equal to constant. Option D, dou square w by dou z square equal to 0. So I hope the question is clear now. It is like simplification of the equation what we wrote in the previous slide. So in this question, what is asked is that for fully developed flow, the steady state momentum balance equation reduces to dash. For a fully developed flow, the steady state momentum balance equation reduces to dash, and options are option A, dou square w by dou x square plus dou square w by dou y square equal to constant. Option B, dou square w by dou y square plus dou square w by dou y square equal to 0. Option C, it is dou square w by dou z square equal to constant. Option D, dou square W by dou z square equal to constant, and option D, dou square W by dou z square equal to 0. So I'll give you a clue actually. It is a fully developed flow and the momentum and the flow is in the z direction. Like we saw, right? It is in the z direction, that is in the L direction. So in z direction what will happen? So W will be a function of x and y. So W will not be varying in the z direction. So W will be a function of x and y. So that is what we have seen in the previous classes also. So like if someone can give answer, it will be okay. So I gave the clue almost, like W is a function of x and y. So we'll see if anyone has given. Okay, option C. Thanks for the answer actually, but answer is option A, because for a fully developed flow we have given that. I'll just show you with the equation. This is the equation actually. Dou W by dou T plus U into dou W by dou X plus V into dou W by dou Y plus W into dou W by dou Z. We'll copy this and put it there. It is in the 9th question. Flow is in the Z direction. Therefore, the fully equation is rho into dou W by dou T plus U into dou W by dou X plus V into dou W by dou Y plus W into dou W by dou Z equal to minus dou P by dou Z plus rho GZ plus mu into dou square W by dou X square plus dou square W by dou Y square plus dou square W by dou Z square. So here W is a function of x and y. So what remains is that fully developed flow, so u and v component velocity becomes 0 and w is not varying with respect to z. So we have 0 in the left hand side and we have minus dou p by dou z, and if we are neglecting the body forces, we have other terms, mu into dou square w by dou x square So this actually leads to this particular term will have one by mu. Okay, 1 by mu into this. Okay, but 1 by mu, so it can be a constant actually. Equal to constant. So dou square w by dou x square plus dou square w by dou y square equal to constant. Option A is the right answer therefore. So we'll see that for fully developed flow, the steady state momentum balance equation reduces to option A, dou square w by dou x square plus dou square w by dou y square equal to constant. Option B, dou square w by dou y square plus dou square w by dou y square. Here it is dou square w by dou x square can also come, but equal to 0. This is false. And option C, dou square w by dou z square equal to constant. Option D, dou square W by dou Z square equal to 0. So our region of interest, that is the flow through the rectangular duct. The rectangular duct cross section is in the xy plane and its length is in the z direction. So L is in the z direction. So the fluid is flowing in the z direction. So we have W component velocity, and that W component velocity is a function of x and y, and therefore we take the equations and we write the balance. So what we are getting is that dou square W by dou x square plus dou square W by dou y square equal to constant. So this is for the fully developed steady state momentum balance equations. So keep that in mind. It is the fully developed flow and the equation has reached the steady state. In other conditions, like all other terms also come into picture, but this particular equation, that is dou square W by dou x square plus dou square W by dou y square equal to constant, is applicable for fully developed flow and the steady state. So steady state only we can cancel out dou W by dou T everything. So I hope it is clear. So ninth question answer is option A is the answer. Sorry. Option A is the correct answer. Now we are going to question 10. Like flow is in the z direction. So this, and fully developed flow, it is W is a function of x and y, and developed steady state flow. So that's it. Now we are going to question 10. In question 10 actually, an appropriate boundary condition at plane D is dash. Option A, dou P, first one, dou P by dou Z equal to 0. Second one, dou W by dou Z equal to 0. Third one, velocity equal to velocity inlet. Okay, so I was mentioning that whenever we are solving a CFD problem, we will give appropriate boundary conditions at the planes, right? Like in the inlet, we will say that velocity is equal to V in some value, and at the outlet, we will give like open to atmosphere. So pressure outlet boundary condition. So something like that we will be giving. So similarly, we are given with three boundary conditions. Boundary conditions are nothing but we are giving some conditions based on the physics, they're based on the actual reality. So like at that point pressure is open to atmosphere, at this point pressure in velocity is equal to this value. So those kind of things which we are giving is known as boundary conditions. So in our case of interest, it is the flow through the rectangular duct, and plane D is nothing but the outlet plane. So we had A, B, C and D plane. A plane is the inlet and D plane is the outlet. B is the mid plane, and C plane is some point 1 ahead, 0.1 times L ahead of the outlet plane. So now at the outlet plane, what boundary condition we will be giving? So three statements or three things are given. First one is dou P by dou Z equal to 0, and second one it is dou W by dou Z equal to 0, and third one it is velocity is equal to V in. So options we will look at it. Option A 1, option B 2, option C it is 3, option D none of the 3. So okay, answers are very only one of things is right. Either first one, second one, third one, or all three might be wrong. So first one, what it is stating, like is anyone giving answer actually? Okay, I'll give out options what it means. First one, it is stating that pressure is constant across the plane D. That is pressure at plane D and after plane D is constant. It is the same. There is no variation. That is what is meaning here. Appropriate boundary condition at plane D is if one is right, it means that right, dou P by dou Z equal to 0. That is pressure is constant across the Z direction, that is along the length. Pressure is constant. Do you think it is right? No, right? It is false. So option A is false. Yeah, option B is the right answer. Option B is the right answer. Like your correct answer is correct. So yeah, option A, it is dou P by dou Z equal to 0. It is not correct because it means that the pressure is constant. Pressure is not constant, but the pressure gradient is constant across plane D actually. Why? Because dou P by dou Z will be like almost constant. Gradient is constant because it is a fully developed flow like by plane D. That is from the outlet, near the outlet the condition will be fully developed flow. So that is the case. And the second option means that dou W by dou Z equal to 0. So this one is true statement because there is no much variation with uh, where that is the W component velocity in the Z direction is not varying. So dou W by dou Z equal to 0. So that is true. Second one is a true condition. And third one, it is velocity is equal to V in. It means that inlet velocity and outlet velocity is the same. V in is nothing but velocity at the inlet. Velocity at the inlet and velocity at the outlet is not the same. So third statement is false. Option 3 is false. So one is false, second is true, third is again false. So coming back to the options, actually option A 1, option B 2, option C 3, option D none of the above. So since second one is the right, option B is the right answer. For 10th question, option B is the right answer. B2, that is dou W by dou Z equal to 0. Now we will go to question 11. In question 11, what is asked is that which of the following statements is true about pressure at the midpoint of plane C? Option 1, pressure is greater than pressure at inlet. Option 2, dou P by dou Z equal to 0. Option 3, dou P by dou Z equal to constant. So options are option A 1, option B it is 2, option C it is 3, option D it is none of the 3. So actually like pressure gradient becomes constant only after reaching the steady state. After reaching the steady state, not steady state, after reaching the fully developed condition, after reaching, I am mentioning that after reaching the fully developed condition, pressure gradient will be constant, not before or at that point. So answer is actually option D, none of the 3. Pressure, we'll see how, like option D, none of the 3. We'll see how first. So the first one is pressure is greater than pressure at the inlet. So all if the flow is occurring because of the pressure gradient, right, pressure would be like fluid flow occurs from high pressure region to low pressure region. So pressure would be lower than that at the inlet, but it would not be high. So one is false. Again, dou P by dou Z equal to 0, it means that it means that there is no variation in pressure. So again it is false. And third is again dou p by dou z equal to constant. It is not true at the midpoint of plane C. After that it will be true, but not at the midpoint of plane C. So option D, none of the three is the right answer. Now we will go to question 12. In question 12, okay, I'll give more detailed expression on for the question 11 in the notes. Like I'll post it when I'm uploading the notes. I'll give more detailed explanation for question 11. Now coming to question 12. Which of the following statements is true about velocity at the midpoint of plane B? Which of the following statements is true about the velocity at the midpoint of plane B? Option, first again three are given. First one, it is W velocity is greater than velocity inlet. Second one, dou W by dou Z equal to 0. And third one, it is dou W by dou Z equal to constant. Option A, it is 1. Option B, it is 2. Option C, it is 3. Option D, it is none of the above. Like B is at the midpoint of the inlet and the outlet. There is no fully developed region or anything at the point B. Like at the plane B, there is no such thing. So what happens is that we cannot say whether the gradient would be 0. Like in general, after reaching the fully developed condition, it would be like 0. But for now, we cannot see. We cannot say, like, because B is at the midpoint of plane B. So one thing which we can say is that, as I mentioned, velocity will be, pressure, fluid will be flowing from high pressure to the low pressure region. So similarly, velocity will be increasing. So W velocity is greater than V inlet will be the right one. So first statement is right. That is W velocity is greater than V inlet, whereas second one, dou W by dou Z equal to 0 and dou W by dou Z equal to constant, we cannot say. So that is the thing. Option A is the right answer. Option A, that is W velocity is greater than V inlet, is the right answer. Now option A is the right answer. Now we will go to question 13. In question 13, which of the following statements is true about Newtonian fluids? So we'll see what statements are given first. First one, it is Newtonian fluid is an idealization. No real fluid comes close to satisfying the assumptions. I repeat, actually, Newtonian fluid is an idealization. No real fluid comes close to satisfying the assumption. Second one, many real fluids are Newtonian. And third one, for non-Newtonian fluids, Navier-Stokes equations are not applicable. So I'll give the options. Option A, 1 only. Option B, 2 only. Option C, 1 and 3. Option D, 2 and 3. Just think about the answer. I'll come back in 2 minutes. Just give me 2 minutes time. Okay. Answer is actually option D, that is many real fluids are Newtonian fluids. For a non-Newtonian fluid, the Navier-Stokes equations are not applicable. Like because we are assuming the viscosity as constant and the equations are framed for non-Newtonian fluids where viscosity is varying depending on the applied shear, we cannot use the Navier-Stokes equations. So option 3 is right. And option 2, many real fluids are Newtonian. Again, it is true. Most of the real fluids that we see in our daily life and also most of the chemicals are many real fluids are Newtonian fluids. Whereas the first statement that Newtonian fluid is an idealization, no real fluid comes close to satisfying the assumptions is wrong, because Newtonian fluid is not an assumption, because many real fluids like water, air, all those things are like Newtonian fluids. So it is false to say that it is an idealization, no real fluid comes close to satisfying the assumptions. So that is wrong actually. So answer is option D is the right answer. That is 2 and 3. Coming to question 14. In question 14, it is mentioned that which of the following statements is true about incompressible flows? Incompressible is an idealization. No real fluid is incompressible. And second one, incompressible flow is a very good approximation for many real flows. Third one, Navier-Stokes equations are not applicable for compressible flows. And options are option A 1, option B 2, option C 3, option D 1 and 3. So I repeat the question, which of the following statements is true about incompressible flows? First one, it is incompressible flow is an idealization, no real flow is incompressible. And incompressible flow is a very good approximation for many real flows. Navier-Stokes equations are not applicable for incompressible applicable for compressible flows. Option A 1, option B 2, option C 3, option D 1 and 3. So the right answer is actually first statement. If we look at it again, incompressible is not an idealization. Like water is an incompressible fluid. Like whichever fluid has constant density, we call it as an incompressible fluid. So first statement is wrong. Second statement, uh, incompressible flow is a very good approximation for many real flows. Again, this is true. Second statement is true because most of the times we can approximate it as incompressible fluids, and density is like not varying, so we can take it out as a constant something something and simplify the equations. And so second is true, whereas third statement, the Navier-Stokes equations are not applicable for compressible flows. This is a false statement. Navier-Stokes equation is applicable for compressible flows. So second statement is false, second statement is true, 1 and 3 are false. So option B is the right answer. Now coming to question 15. So question 15 is the last question for today's this week 3 problems. I have one more problem from last week actually. But yeah, first we will deal with this. Which of the following statements is necessary in CFD simulations of the fluid flow problem using the Navier-Stokes equation? Which of the following assumptions is necessary in CFD simulations of a fluid flow problem using the Navier-Stokes equations? Option 1, laminar flow. Option 2, boundary layer flow. Option 3, fully developed flow. Like coming to options: option A 1, option B 1 and 2, option C 1, 2 and 3, and option D none of the above. So So answer is actually none of the three. That is, these three assumptions are not required for solving the Navier-Stokes equations. Like laminar flow or turbulent flow, it works. Boundary layer flow or fully developed flow. These approximations simplify the equations, but it doesn't mean that these assumptions are necessary for the CFD simulations of fluid flow problem with the Navier-Stokes equations. So none of the three is the right answer. And coming to answer, it is option D. None of the three is the right one. And these are the problems from week 3 actually. I have one more problem from week 2, like question 13. Like that time I actually made some wrong statement in the problem, like answer discussion, during answer discussion. So I told like I would rectify it in the next class. So for that is this problem. So comparing the finite difference method and the finite volume method for fluid flow problems, which of the following statements is true? First one, both methods would give same results for fine grids. Second one, for simple geometries, FD is preferable. And third one, it is FD is preferable for irregular or complex geometries. So comparing the finite difference and finite volume approaches for fluid flow problems, which of the following statements is true? So the first statement, both methods would give same result for fine grids. Second one, for simple geometries, FD is preferable. Third one, it is FD is preferable for irregular geometries. So options are A 1 only, B 2 only, C 1 and 2, D 1 and 3. So answer is option C, that is 1 and 2 is the right answer. Because when the grid size is very fine, both the methods would give the same results for very fine grids. So option C, first statement is right. And second statement, it is for simple geometries, FD is preferable. That is, finite difference approach is preferable, whereas finite volume approach is preferable for irregular geometries. So this is what is given, like finite volume method is preferable for irregular geometries, primarily due to the ease of grid generation when we are dealing with the irregular complex geometry, and refinement will be better when we use finite volume approach for the complex geometry. And for very fine grids, the discretization error becomes so small that both finite difference and finite volume will be expected to give the same results. So that is why our answer is option C, that is 1 and 2 is the right answer. So yeah, that is for today's class. If there is any doubts, let me know. We can discuss now. Four. Okay. If you have any feedbacks, you can tell actually. Like these things needs to be improved, or these things are not clear. Anything like that, I can change in the next class. Okay, okay, then we'll see again in the next class. Again at the same time. Thank you. I'll upload the revised PPT. Revised in the sense I'll give more explanation for the answers and upload the answers. You can check that also. Thank you. If there are any doubts, we'll discuss, or else we can close the session actually. Thank you. I'm just stopping the recording for now.